Today we're going to talk about a different test called a chi-square test. And um, the symbol that's used is the Greek letter, okay, chi, sometimes referred to as chi, but chi-square is a statistical test. And I'll write it out here. And it's similar to what we've been done, a few changes, some different ideas, but basically, a lot of the stuff is very much the same as when we were looking at things like, correlation and so on. And um, with correlation, we were comparing two variables, two different variables. We had one sample uh, or one group, and we measured twice. So we had one group, say, of individuals that had two scores, a test score in math, test score in English, and we said that we could compare, but we said that correlation was a comparison of two quantitative variables. So we needed numbers to be able to um, do the computations for correlation coefficient, that sample correlation coefficient R that we worked with. And chi-square almost sounds the same. It's where you have a comparison of two variables, but it's a comparison of two qualitative variables. Okay. Okay, two qualitative variables. So let's say that we had some thoughts about gender. We had a group of people, a group of men and women, and we wanted to know what their favorite car color was. And you may be a manufacturer, and of course, if you're going to sell cars, one of the things you would like to know is, what kind of colors do people like? What color of cars do they like? So we could run a chi-square test, and we could compare. Again, we would have two qualitative variables. Gender is qualitative. We could break that down into male, female. Remember, qualitative is when we put them in groups, and the groups differ by some non-numeric value. And so gender could be male, female. And then um, we could talk about the typical car colors. Color would be our other variable, which is also qualitative because colors are not magnitudes. We have blue and green and red and yellow and white and so on. So that would be a good chi-square test. Um, and that in particular would be called a test of independence, though. And we have two different types of tests. We have the test of independence, and we also have a test of, all right, goodness of fit. Let me get my eraser out here, write this differently. A goodness of fit test. Okay, so we're going to do two separate videos on these because this is a little lengthy, but I want to go slow and talk about all the details as we go through. So now the goodness of fit test is kind of like what it sounds. It's how good does our data fit some predetermined distribution. So it's kind of like hypothesis testing, for one sample uh, parameter. So if we say, one sample mean like, you know, Dodge Caravans, the four cylinders get 28 miles to the gallon on the highway. And then we had some value that we went on and collected a sample, and we wanted to know how close our sample miles per gallon came out to be on average to the overall average of 28 that's claimed. So we were in a sense seeing how good our data fit the hypothesized value, and it's kind of like what's happening here, except with qualitative or categorical data. So the difference between these two tests here is that the test of independence, typically we don't have any predetermined values that we're comparing to. The goodness of fit test, we do have predetermined values, and there's lots of other tests that people break this down into, but in general, this is the idea for chi-square. Whether you have predetermined values that you're comparing to, and again, two qualitative variables here, and also for the goodness of fit test, we have something already predetermined. So let's go ahead and I'll talk through it as I uh, get this stuff going. So I'm just going to clear this canvas, and um, I want to bring up a image, and I had this pamphlet from Mars Company, M&M, Mars makers of M&Ms, and there's lots of data on here about how they color those different types of M&Ms, like the plain M&Ms and the peanut M&Ms and so on. And so I just want to pick one of these, and so right here, uh, we'll see it says, on average, the new mix of colors for M&Ms, plain chocolate candies will contain, and they give us some values that are supposed to be there when we get those plain M&Ms, right? So 30% brown, 20% yellow and red, 10% orange, green, blue, and so on. So um, we're going to use this data. Let's see if we can get that up there. And I've got to get this thing. Oops. All right. I guess that just goes on. All right. So what I need is a table. And uh, with chi-square, we have what we refer to as contingency tables. So they list counts. And so I want to get those counts listed up here. And I'm going to start, let's see, right here, and draw a line there. And I'll just draw a line here. Seems to be good. In the middle. And let's kind of put another one in there. And we should, this should be good enough. So I'm going to need some lines the other way. And what I'm going to do here, all right, so these up here are going to be my observed values. And it would help if I get that spelled correctly. There we go. Okay, the observed. And for some reason, I must be too close to the ruler. There we go. Observed and expected. expected. Okay. And on the colors, I had the orange, green, blue, right? Brown, yellow, red, orange, green, and blue. So we're gonna have to get those. And we'll build our table, and so we're creating again. We have these groupings, right? This this is a table. This is 2 rows. So far we have 2 rows. We're going to have 6 columns. We got 4 and 5 and 6. Okay, let's carry it. Okay. Okay, I'm gonna put this thing away, and all right. Well, for some reason my eraser is not working. Okay, I gotta use the other pen. All right, and that's right. All right. So the data that we were given, uh, remember that we said that brown was 30%. So if you get a plain bag of M&Ms, it should have 30% brown in it, right? And then they said that 20% yellow and red. So yellow, 20%, red, 20%, 10 orange, green, and blue. Okay, and these should add up to be 100%. So 30, 50, 70, 80, 90, and 100. So we got that. And then what we're going to say is that we had a bag. Let's say we bought a big party pack. We have a bag of n equal to 200. Okay. And this thing is 2 rows by 1, 2, 3, 4, 5, 6, right? For each one of these colors. So this is a 2 by 6 table, and we'll see why are we worried about that. And I get this. We do need this. So 2 rows, 6 columns, and this is going to be brown, yellow, red, orange, green, and blue. So the expected, all right, if we have 200 M&Ms, 30% of those are going to be brown. So 30% of 200, 0.3 on 200. So it's going to be 60. We expect 60 of them to be brown. And again, that's given. 20%, so 40 should be yellow. 20% are red, so 20% of 200, 40, 10% of each of these last ones. So 20, 20, 20. We're taking this times this, the sample size, right, to get these counts in here. and this all totals up to 200. All right. Now then, once you get that set up, again, we want to collect some data. So let's say I got this, and I break it open and I actually count how many brown, yellow, red, orange, green, blue in there, right? So I'm going to um, put that in there, and let's say that the brown comes out to be 65, and the yellow comes out to be 48. Red, we'll say there's 40, comes out exactly the way it's supposed to. The orange, there is 10, 22, and then you notice I had this kind of free played here, but now I don't have a choice because there's 200. I can't make this number up. So if I take the 65 plus the 48 plus the 40 plus the 10 plus the 22, I get 185. So far, this is 185 total. That means this has to be, right? I don't have any degrees of freedom there. I don't have a freedom to vary on that, so this has to be 15 total students. But with chi-square, it's categories, the sample size. This does not determine the degrees of freedom. Okay, degrees of freedom is the number of rows minus 1 times the number of columns minus 1. That's LUMN. Columns minus 1. Okay. So degrees of freedom, then in this case is, so here we have 2 minus 1, 2 rows, 6 columns. So degrees of freedom equal to 2 times, or 2 minus 1 is 1 times 6 is 5, so we get 5 degrees of freedom. Okay. And again, we're going to need this. This is going to help determine how much of a difference is going to be considered a statistically significant difference. Okay, now here's, we got our data, and we're going to actually look at this two different ways, because the newer calculators will do the chi-square goodness of fit test. The older, not old, I mean just, within recent years. So there's a lot of students, it's about a third right now. Usually when I ask my classes who has the goodness of fit test, maybe about 2/3 of them say yes and the other ones don't. So we need to take a look at this, and this chi-square goodness of fit test. So this is a chi-square, the sum, okay, of the observed minus the expected values squared divided by the expected. All right. So what does that mean? This is that sum. So we add up these things. So let's go ahead and do that. What we're doing is we're comparing, we're going to look at each of these, because the test is a summative test. It's actually taking the differences from what we observed and expected from each of the colors and kind of adding them all up to give us one test statistic. So 65 minus 60 squared over 60 plus. So these are for those students that do not have the goodness of fit test on their calculator. I'll show you where that's at in a minute. And 48 minus 40 squared all divided by 40 plus 40 minus 40 squared, all divided by 40, which I'm getting these numbers from comparing this to this here, this to this here. We're looking at how big a difference the colors were to what we expected. We're doing each color, right? Red came out exactly the way, so when we take 40 minus 40, we'll get a 0, which means no difference, right? Plus 10 and 20. So 10 minus 20, well, it's negative 10. We square it to get rid of the negative, over 20 plus 22 minus 20 squared. So see, that's not going to add or contribute much to the total. Again, I just made that for some reason. 15 minus 20 squared over 20. So again, this is a 15, which we're getting from right here. And then you got to do all those calculations, and I'm going to do that in just a second, but we're going to do it on the calculator for both, and then I'll continue with this. But let's go ahead and go to the calculator. So we're going to go to, let's clear this out. We're going to go to Stat, Tests, and we're going to go down almost to the bottom. Okay, see this chi-square, GOF, goodness of fit test. So this calculator has that goodness of fit test. So what I need to do is go into Stat, Edit. Let's clear these lists. Clear, Enter, clear, Enter. All right, so the observed goes in L1. So 65, Enter, 48, Enter, 40, Enter, 10, Enter, 22, Enter, 15, Enter. Okay, so we got 1, 2, 3, 4, 5, 6. All right. All right. So the expected goes here. So we've got 60, Enter, 40, Enter, and so on. So we're going to put all these in. And 3 of those 20s to get in there. So, all right, so let's go back to Stat, Test, Goodness of Fit Test, Enter. L1 and L2s are observed and expected. Degrees of freedom is 5. We figured that out. Subtract 1 from this, subtract 1 from this, and multiply. 1 times 5, 5, and calculate. All right, so 8.4. So whether you do it with the calculator or by hand over here, we're going to get the same number. So this is what, 8.47. This is our test statistic, okay? And you get a p-value. P is 0.13. So we get a p-value, right? And you notice you don't get a lot from this. There's no means or standard deviations, right? We got categorical data with some counts, their proportions. We're working with percentages. And degrees of freedom is 5. So we're going to put that also here. Degrees of freedom, 5. We know that. All right, so I'm going to get rid of that over there. I need some room. So I'm going to get rid of this. And remember that it's okay. You're only going to be one problem that you have to do on the test. Some people, they want to run out and get a calculator or whatever, but this isn't that bad. It's just one calculation. You'll get exactly the same here. Now, how do you get the p-value? This p equal to 0.13. All right, so remember in your calculator, this test is somewhat normal, but it's right skewed, okay? And it's also a right tail test. When we refer to hypothesis testing, we always had to have either right or left or two tail. Well, this is going to be easy because we're only going to do right tail test with the chi-square. This starts at 0. Since we're squaring all these numbers, it's never going to be negative, so we don't need anything over here. And it's going to be 1. Okay. So, see if this is same as this divided by this is going to be 1. So if these were all, then theoretically, again, I know we're going to add these, but we would divide them by, remember we have degrees of freedom and there's adjustments on the bias and so on. So theoretically, it's kind of a 1, top number, or the number observed divided by the expected would be 1, 100%. Okay, so p-value. Now, I'm going to also erase this to get some room. And that's not erasing. Don't worry about it. Okay. So if you don't have the goodness of fit test, how do we get the p-value? We know we got the critical value. So we got that. And that was the that was this here, the 8.47. Okay. So this is 8.47 here, right? And we need to find the area under the curve, just like we did before. So this is kind of way back when we started to work with the normal distribution. And we were looking for probabilities by looking at the area under the curve. So if we want the area under the curve from here on out. And if you go back to the calculator, right? Let's go back to this calculator and move this thing over here. All right. Now, if I go in, if you remember, how did we find area under the curve? Well, we went into distribution and we did normal CDF. Well, we don't, when this is on a normal curve, we would be able to do that. So here's with our 7 chi-square PDF, chi-square CDF. So we want to come down to 8 chi-square CDF. And then the lower, so what we have is the we have the chi-square CDF, and then this is your starting point, just like before. We had to know our boundary values, and then this went off to infinity, which was E99, and then our degrees of freedom, which are 5. Okay. So let's go into calculator again, and lower is the 8.47. Okay. The upper, E99. Our degrees of freedom is 5. And then we paste. So if you don't have the calculator that does that stuff and you just get this to show up first, you just plug that in. So we'll get that, put that in. And then we're going to enter again. And if you remember, our p-value was 0.13. So we got to 0.13. So whether you do it this way or the other way, it will come out exactly the same, 0.13. So if we were running a hypothesis test, right, our null hypothesis, okay, is that it's long. It's a long hypothesis. It's that the observed and expected for the browns would be equal, and that the yellows would be equal, and the reds are equal, and orange are equal, and green are equal, and blue are equal, and that none of them are significantly different from each other. Or the alternative would be that at least one comparison is significant enough from each other to cause the whole table to go and show a big difference. See, this number, this 8.47, came from adding up. Remember? The differences here, the differences here, the differences here. Of course, we squared and divided. So we'd get a few here and a few here and a few numbers here and a few numbers here. When you added them all up, you got a total of 8.47, or the sum, right, of the observed minus its expected squared divided by the expected. So it's a summative calculation. So that means that one grouping could be big enough to cause the whole table. And then you have to do follow-up or post-hoc analysis to see which ones were and weren't. Now, we don't have to worry about that though, because 8.47, it's not very big. It's not a standard error. It's just a cumulative value. We still look at the p-value, right? Remember, our golden rule in hypothesis testing basically is if p less than alpha, reject h sub 0. H sub 0 would be that the M&Ms have all the colors that are supposed to be in there just the way we expected them, right? That's what we're saying. And can we reject that? Now we know it's not going to be perfect. Some of these colors are different than what they're supposed to be. Look, that's off by 5, it's off by 2, that one's off by 10. Well, with 5 degrees of freedom, it's a decent table, and we need to have enough, right? We have to have beyond a reasonable doubt in a sense to reject, and we don't, because here's p-value 0.13, right? 0.13 is greater than 0.05, and again, the standard's kind of 0.05, regardless of 1%, 5%, 10%. This is still larger. We would still, in this case, fail to reject h sub 0, or that the colors that we got in our bag of 200, right, we're just going to have to say that, yeah, they came out pretty much what they said, right? We don't have enough evidence to reject that. We only collected a small sample. We're making a judgment about the population. We can't extend these ideas beyond what they really, are likely to be telling us. So, but that is our, again, goodness of fit test. So remember that. Check your calculator right away. That's the key to this first one, is go into, stat, test, and go down. And again, everybody's going to have the chi-square test. This one right here. Everybody has that one. GOF test, maybe about a third of you don't. If you don't, you got to follow what I did with that big long calculation and just everything else is the same. But if you have the GOF test, yeah, it cuts down a little bit of the work. Cuts down a little bit of the work because it gives you the test statistic, right? It gives you this automatically. It gives you the p-value, and it gives you the degrees of freedom. So as long as you put these numbers into the editor correctly, then it's very easy. It's a right-tailed test, right? We don't have to worry about. We're over here on the right. Everybody's doing right-tailed test. Could you use this? So yeah, there's always situations. Lots of different applications for chi-square. It's a very popular test. But if you're working with categorical variables and you have clearly categorical variables, one of the big mistakes with chi-square is people like to create categories where things are really quantitative and they mess things all up. But this is good. Predetermined percentages. We were able to calculate what these counts would be. We compared them. The differences will always be there. Summatively, were there big enough sum of all those differences added up together? No, right? Because our p-value was 13%. We need that p-value to be really 5% or less when we're working with, trying to reject. Okay, so that's it for the chi-square goodness of fit test, and then we're going to look at the test of independence in the next video.